All right, so I guess Vanya will tell us about the explicit problem on K-stability of Fano varieties. Please go ahead.
Okay, thank you very much. So basically, since I recently gave talk in Salt Lake City about K-moduli, I try to organize my talk in such a way that it's completely disjoint from what I spoke in Salt Lake City. So basically, it's like a semi-survey talk, and I listed a lot of like open problems and something. So less, and some all problems going to be very, very explicit. And I didn't actually have time to proofread the slides. So if you spot some typo or mistake or something, please let me know. Maybe in the chat, or maybe better even by email, because chat usually disappear after the meeting. Okay, so let me basically start with Del Pezzo surfaces. So classification of, say, Duval Del Pezzo surfaces is a classical topic, which is basically started from the works of Duval 100 years ago, and then some special particular results was actually obtained very recently. So, and due to combination of efforts of many people, and we got complete, more or less, we know everything about the case semi-stable and K polystable Duval Del Pezzo surfaces. Del Pezzo surface Duval singularities. Duval is canonical Gorenstein in this case. So picture is very clear. So basically, which can be easily explained from the relation between the normalized volume and degree and delta invariant, but basically this is final answer. So which Duval Del Pezzo surfaces are K semi-stable? Answer is very simple. I mean, it looks simple, so it's okay. Okay, so this can be proven in different ways, but for example, recently my PhD student, Lena Denisova, who actually yesterday got a job in Glasgow, she computed delta invariant of all Duval Del Pezzo surfaces, and her result implies this theorem. So it's basically all cases when delta is bigger or equal than 1. Yeah, so it's very explicit. But her motivation was not to reprove this theorem, it's a side effect, but her motivation was basically to use this for inductive purposes for threefolds, because usually you can reduce some case stability problems for threefolds to surfaces, and quite often the surfaces is Duval Del Pezzo. If they're not Duval, it's more complicated. Okay, so this is just basically the list. Okay, surprisingly, if you compare this theorem, it reminds a little bit absolutely different problem. I'm not sure that there is any relation between them. There's some relation between them, but not direct. But I think it's of interest. So this problem is not related to K-stability. It's actually a problem came from affine geometry. So you take it can be stated for any algebraic variety. Most interesting is for Fanos. But for Del Pezzo, it's very explicit. You take a Del Pezzo surface with, say, KLT singularities, and we defined anti-canonical polar cylinder in Del Pezzo. It's basically cylinder. It's a product of A1 and some affine curve. So it's a affine subset. But such that the complement is the support of the anti-canonical effective divisor, Q divisor. And surprisingly, existence of such cylinders implies the additive group action on the cone of such surface in pluri-anticanonical embedding. And this is how it's related to affine geometry. So for Duval, we have this very simple theorem. So if you have Del Pezzo surface with Duval singularities, that it doesn't admit anticanonical polar cylinder, if and only if we have this condition. So in some sense, it reminds a little bit K semi-stable. So in particular, in all these cases, is K semi-stable. So for a while, I thought maybe there's a relation. Maybe if you don't have anticanonically polarized cylinder, the surface of Fano should be always K semi-stable. But this has turned out to be not true. Last year, Kim and Kim constructed actually counterexample, constructed very explicit singular Del Pezzo surface, which is actually many of them, actually all of them hypersurfaces in the weighted projective space, which are K unstable, but without polar cylinders. So, okay, but anyway, this is, I just put it just for curiosity. Okay, let's go back to K-stability. So classification of description of K-Moduli for smooth Delphi surfaces and the Duval limits, K-polystable limits, has been done by Adaka, Spotty, and Sun, 2016. And I mentioned the Moduli part in Salt Lake City, but this is I just focused on Duval. Okay, yeah. So classical cases, Mukai-Mabuchi, K-polystability is basically means it's a, for the Duval Delphi surface of degree 2, 4, it's should be a complete intersection of two quadrics which simultaneously diagonalizable, and the singularities is a 2A1, 4A1, or smooth. So this is basically classical JIT construction. And these surfaces form the whole K-moduli space in this case. For cubic surfaces, this is started in the works of Ding and Tian and finished by Adaka, Spotty, and Sun. This is again JIT picture, A1 singularities or 3A2. For degree 2 Delphi surface, it's either A1 or A2 singularities, or it's given by very explicit equation. So basically, this symmetric surface which has two A3 singularities and maybe additional A1, and it has a big automorphism group C star semi-direct C2. And a similar picture we have for degree 1 Duval Delphi surfaces. Yeah, so basically it's either A1, A2, A3, 4, A5, A6 singularities, or it has two D4 singularities, or it has A7 singularities, but different from that one. Geometrically, this is this bad Duval Delphi surface has A7 singularities, but when you take a double cover of P112, its ramification divisor is irreducible. So it's K-semi-stable, but not K-polystable. Okay, so basically this gives complete answer for K-semi-stability, K-stability, K-polystability for Delphi surfaces with at most Duval singularities. And if you consider non-Duval singularities, we actually don't know much. So first of all, Delphi surfaces with quotient singularities not completely classified. I mean, we have a lot of partial classification results. So one of the first results in this direction was the result of Nikulin and Alexeyev and Nikulin, which is actually originally published in 1988 in Russian, but it was unavailable. So after many years, they completely rewrote it and published it as members of Japanese Mathematical Society. In this big paper, they classify all Delphi surfaces of Bernstein index 2, such that twice anticanonical divisor is Cartier. Independent proof was done by Noboru Nakayama in 2007 without using theory of K3. So basically, Nikulin and Alexeyev consider double cover of this Delphi ramified and twice anticanonical curve. So it's a K3 surface with Duval singularities. Okay. So, and relatively recently, but already like almost 8 years ago, Kenta Fujita and Kazunori Yasutake actually classify Delphi surfaces of Bernstein index 3. Surprisingly, in all these cases, there's no results about K-stability. No one studied K-stability of these surfaces. I mean, this is a nice set of objects. So this Delphi surfaces which are as close to Duval as possible, so like index Bernstein index 2 and 1. And I think it's going to be a nice problem to consider, but it's absolutely open in this case. Okay, but I'm pretty sure it's going to be this problem going to be studied soon. A lot of results, we have a lot of results, but more or less like computational in some sense about Delphi surfaces with cis direction. If you have a Fano variety with a torus section of dimension 1 less, it's usually called T varieties. And there's a big research group in Germany who studied Fano varieties with these properties. It's like Klaus Altmann, Jürgen Hausen, Hendrik Suess, and the former students. So basically, recently they studied K-stability of Delpezzo surfaces with this direction, but they didn't get complete. In this case, we actually have a nice criterion, very similar to Toric, but because we lack classification, they only obtained like partial results using computer. So first, in the case when Picard group is Z, there's very explicit algorithm how to find such Delpezzo surfaces when you fix Gorenstein index. And you can run this algorithm and you can apply K-stability criterion, which exists for T varieties. And this is done in this paper. And basically, there's a lot of experimental results. So basically, they just run this algorithm for thousands of families, and then they check which one is K-polystable or not. So yeah. So just for curiosity, I put it. This is for Toric. For Toric, it was of course known long time before and available on basically online. You can use this web page GRDB and just, for example, this is example online. So you see that if you take a Toric case and this is the number of polytopes which correspond to the Toric surfaces split by indices. So index 1 is Duval. We have exactly 16 Toric Duval Delpezzo surfaces. Only 5 of them are polystable. And we can see that the number of Toric surfaces grows quite a lot with the index, but number of K-polystable one remains roughly the same for each index. So, okay. And in some sense, similar picture for Delpezzo surfaces with this direction. Okay, good. Then another nice big subclass of Delpezzo surfaces with quotient singularities are given by hypersurfaces in weighted projective space. And basically, the first study of these surfaces was done by Jennifer Johnson and Janusz Koller quite long time ago. So basically, if we fix quasi-smooth, okay, wait, there's a question in the chat. Valeria, not Valera. Okay, so, yes, Valeria is not Valera. I often address, I just do it automatically. When we speak with Valeria, I usually address him as Valera. Okay, good. So if we have quasi-smooth, what are Johnson-Koller surfaces? It's quasi-smooth, well-formed hypersurfaces three-dimensional projective space, which of index 1, but here index is not Gorenstein index before. Sometimes it's called amplitude. Yeah, so basically this is like a index and the Fano index and the class group. Yes. So Jennifer and Janusz completely classify them. So basically this is classification. And we have one infinite series. And then we have a few sporadic examples. So in many cases, we don't have moduli. It's basically just one quasi-smooth member. In some cases, we have some moduli. And actually, in some cases, also small deformation, you can actually consider deformation of some of the surfaces and you get non-hypersurface. I mean, there's very few cases. Yeah, and only 3 of them are smooth. Because three families which contain smooth members. So this one, 1113, this is a cubic, and then this is a Delpezzo degree 2 and Delpezzo degree 1. All others are singular. And we know all about the K-stability. So basically, all of them are K-stable. This is basically a series of papers. First results by Jennifer and Janusz, and then there was paper by Karolina Raujo, and then was some paper by me and Kostya Shramov and Jehun Park. And then actually we finished it basically just a few years ago using evaluative criterion. Okay, and but actually surprisingly, no one till now studied the singular degenerations and no K-polystable, and no one can study the moduli. Of course, except for Duval case. For Duval case, we know the K-polystable limits, but for non-Duval case, this is not done. but it's actually, I think it's interesting problem. Okay, good. So you can also consider higher index. So in this case, when Johnson and Kohler proved the theorem, they actually wrote the algorithm how to find all this weight. And this algorithm was adopted by Eric Paramuro when he actually was an undergraduate student. And basically, he wrote a program which one can freely use, and it's available in his paper. And basically, you can find the list, including infinite list, infinite series for every index. Yes. So, for example, when index is 2, you have much more infinite series, and you have a bit more sporadic example, and one infinite series which depend on 2 parameters. Yeah. But most of so our expectation first was that maybe in this case it's also all case polystable. They cannot be case semi-stable because some cannot be K-stable because some of them has infinite automorphism group. But actually, many of them are K-unstable. It was, for example, one can see that if you have this double series with the 2 parameters, if these parameters are not equal, using evaluation criterion, you immediately prove that they're unstable. So this problem was completely solved for index 2 by Kim Won and Vishwanathan 2 years ago. Basically, they just went through the list and apply evaluation criterion and use basically estimation for delta invariant to prove K-stability. So it's almost always K polystable, except very few cases. And recently they did the same for index 3. There's actually small typo in the main result of this paper, which is available online, but they will correct it. So basically, they in the main theorem they added one case which is actually K semi-stable but not K polystable. Okay, so answer is very simple in this case, and it's actually looking at on this, we can actually expect that if first weight of the weighted projective space is bigger than 2 or 3 times index, then this is surface going to be always K polystable. May probably if and only if, and this is the conjecture. And this 2 over 3 here, it actually comes from alpha invariant of Tian. So if this inequality is not true, then alpha invariant is less or equal than automatically less equal than 2 over 3. So Tian's criterion is not applicable. So, but it also comes from some experimental data for the lower indices. And as far as I understand, they're currently working on this. Okay. Similarly, you can consider weighted complete intersection. So we know from theorem by Chen that if you have this weighted complete intersection, then it's enough to consider. So if it's not one of the hypersurfaces is not a linear cone, then it's basically can only be a dimension 1 or 2, either hypersurface or dimension 2 for surfaces. And we actually know the classification, some kind of classification by Mayansky, but the paper is actually unpublished. It's old paper, 6 years old, and I think he actually quit math, but we have classification. And K-stability only done in the case when index is 1. If index is 1, it's K polystable. And this is a theorem by Kim and Ji-Hoon Park. And for higher indices, it's been unexplored. We have classification, but as far as I know, no one studied K-stability of these Delbezza surfaces for index bigger or equal than 2, and we can expect that probably we don't have such simple answer for higher indices. So probably I expect some of them are going to be unstable. Not I expect, I mean, it's for large index definitely, but say for index 2, maybe few. Okay. Another nice class of Delbezza surfaces with quotient singularities are when they have current 1, and this is usually called Q homology planes. Actually, this surface has been studied by Sean Kill and James McKenna a long time ago in 1999. And in Memoirs of AMS, it's like a paper book, quite kind of big. Yeah, and they obtain partial classification. Okay, partial, I mean like up to finitely many families. So in some sense, in some sense they obtain classification of all, almost all surfaces whose alpha invariant is less or equal than 1. So in some sense, all non-K polystable should be here in the classification, but the classification is not very, like, how to say, easy to use. So yeah, so K-stability, for example, has not been studied, but in many cases, in this book paper, this paper book, they presented a lot of actually surfaces without tigers, but surfaces without tigers in this notation means that the alpha invariant is bigger than 1. So in particular, they are all of them K-stable. So it's, in some sense, K-stability appears implicitly in this book 25 years ago. Yes, and in 2009, actually a bit earlier, it was published in 2009, Grisha Belousov proved that number of singular points cannot be 5, and which was actually conjecture of Janusz. And Janusz proved it cannot be larger than 5. And so we basically have for number of singular points, we have few possibilities, 1, 2, 3, 4. Okay, 0 is not interesting. So when number of singular points is 1, actually such surfaces has been classified in 2014. And very recently, James' student, Justin Lassini, classify all such surfaces. But again, classification is, it's not just a list, so it's sort of kind of algorithmic, but it's a nice classification. But so far, no one uses classification to study K-stability. And the result of Justin is very recent. I think it just published maybe a year ago, or maybe 2 years ago, or very recent. Okay, so basically, this is almost everything I know about K-stability of like the Delpezza surfaces and some classification type results. So I think actually it's a lot of problems here to study. So let's slowly move to threefolds. We all know that smooth finite threefolds classified in 105 families. And for 87 families, all K-polystable smooth members are known. And this is including families without K-polystable members. And this is actually collective efforts of many, many people over the last 30 or maybe even 40 years. 30 years, 34. So for example, first results of Nadil, I think it was in 1990, 24 years ago. This is the remaining 18 families. I will mention them in more details. And I really want these families to be done. I really want to find all K-polystable Fano threefolds in these families. And but it's probably going to require efforts of many people, but I hope it will be done soon. In particular, we know due to Kent that 27 deformation family does not have K-polystable smooth members, and we know that all general members of the remaining families are K-polystable. So yeah, okay. So just this is a screenshot which I usually put in the slides. Just basically, if someone later read the slides and want to refer to the numbers of this family and see which family is which. So this is basically a screenshot from Fanography webpage with description of all these Fano threefolds, just in case someone gonna use this slides later. Okay, so the simplest, let me consider just one example. Simplest examples are given by smooth Delpezza threefolds. Delpezza threefolds are basically Fano threefolds whose anti-canonical divisor are divisible by 2. We have very simple classification, which is basically due to Fujita, I guess, classical Fujita, not Kenta. And it was they were classified long before Fano threefolds. And of course, classification resembles classification of Delpezet surface. And all of them except one are polystable. And again, this is the efforts of many people, not just one. It's just not just one paper. Okay, and moreover, we also, except one family, we also know the K polystable limits. Namely, if it's degree 1, so this sextile P1, 1, 2, 3, we don't know K polystable limits, but I'm pretty sure that people are working on this. And for degree 2, Kenyasher, Kirsin Devlemenko, and Yuchenliu basically describe all K polystable limits. And it's very, if you only consider, so it's basically, it's very explicit. I will also mention this in Salt Lake City. And for degree 3, it's a classical theorem by Yu Chen and Chen Yang that K-stability for cubics coincide with JIT stability. And for equal 4, it's done earlier by Cristiano Sputi and Song San. Okay, so this is just an example. So here we basically, for smooth threefolds, here we know everything. For singular, we don't know only in these families for degree 1, but I'm pretty sure it's going to be done soon. Okay, so what are the remaining families? So this is the remaining families, which we don't know answer completely. 18 deformation families, and I red means that the family, we know that the family, if family is marked red, we know that this family definitely contains not K-polystable members. But we actually expect that all smooth members of these families are K-semi-stable. This is expected, but it's open. And we know a lot of partial results for each families. And we know the general member of each family is a K-polystable. And let me just briefly basically go through each of these families to see to which extent we can actually push existing techniques to some limits to prove K-stability. Or just basically, let me maybe remind how it is proved that general member is K-polystable. So for example, family 1, 9. 1 means Picard group Z, degree is 18. So in the book, which we wrote over the COVID, basically what we did in this case, we constructed, it's actually an interesting thing. So we wanted to prove that general member is of this family is K-stable. But surprisingly, we couldn't find, it would be enough to find one such example, K-stable smooth example. But we were unable actually to do this. We don't know any single explicit smooth example which is K-stable in this case. It's possible to construct, but it's much simpler actually to construct a singular K-stable example in this family, not the smooth one. So this is the idea. You take complete intersection of two quadrics. You can basically take any of them, but you can just take symmetric one. This one has a lot of symmetries. And you take a line in a twisted cubic here. So you take a special section by P3, such that it cuts this complete intersection into singular curve, which is consists of twisted cubic and its second line. And then you blow up the twisted cubic. And when you blow up twisted cubic, the resulting threefold is weak Fano threefold. It's anti-canonical divisor almost ample, but it's intersect with a strict transform of the line by 0. So you contract it, yeah? You contract this line. So I forget to mention that you contract the line. Yeah, you contract the strict transform of the line, and what you get a singular Fano threefold with one isolated Gorenstein terminal singular point. We didn't check the normal bundle, but I'm pretty sure it's ordinary double point. And its degree is 18. Picard is Z. So by general Novikova result, we know it can be smoothed to smooth Fano threefolds with Picard group Z. So it can be smoothed to one of the admits small deformation to the smooth Fano threefold in family 1, 9. But in this case, group is automorphism group is non-trivial, and because we actually started with very symmetric example, we have two action of Z2 times Z2. In particular, this group doesn't fix points, and which can be actually used. So it simplifies life a lot. So basically, if we know example in this family, in a smooth one, say with a group that doesn't fix points in threefold, then it's not difficult to prove K polystability. But we couldn't construct such example. And so we constructed singular one. We couldn't construct smooth one. And using this, we proved in the book that it's K-stable. So in particular, general threefold is also K-stable. But we expect conjectures, all of them has to be K-stable. But in the moment, we cannot prove this. So in the recent preprint with Hamid Aban, Takashi Kishimoto, and Frederick Mangold, we actually proved some strange version of this theorem. We proved that if you have a form of smooth Fano threefold in this family that has no points in a given field, that it's also K-stable. So using this, you can actually construct a lot of explicit examples. But again, we didn't construct any examples. No, actually we did. No, we construct one explicit example, so it's actually available on, in our paper. Yeah, but yeah, we did one. Okay, good. So family number 110, probably the most famous family. People sometimes call it V22, X22. So the simplest way to construct a case-stable example in this case is consider Fano threefold in this family with a lot of symmetries. But in this case, it's quite straightforward how to handle automorphism group of the threefolds. So, due to construction, thanks to construction due to Mukai. So let me briefly remind it. So we fix quartic curve in the plane. In this case, it's a clean quartic. And then you consider the space of this polar hexagons. So namely, you take 6 distinct lines, take the linear form, and we say that the union of this line is a polar hexagon to C if equation, defined equation, so it's small f, defining equation of your quartic is the sum of 4th powers of this linear form. Then you consider these hexagons as an element of Hilbert scheme of 6 points in a dual P2, and you take a closure of all of them, which are polar. And basically, Mukai proved that if your curve, quartic curve, satisfy some very explicit conditions, non-degeneracy condition, then X is a smooth Fano threefold in the family 110. So these conditions can be checked in this case very explicitly. And we get that this is a smooth Fano threefold. Construction is functorial. In particular, we get a smooth Fano threefold with the action of the big group. It's an automorphism group of this clean quartic curve. It's PSL27. It's a simple group of order 168. Using this, it's very easy to prove, basically immediately, that this threefold is K-stable. So this implies that general threefold is also K-stable. And of course, there are other constructions, but in general, K-stability is not known for every smooth member. We also know that there are members which are not K-polystable, and there's a conjecture by Donaldson, which threefolds in this family polystable and which are not, and we expect all of them are K-semi-stable. Conjecture is in our book, so I didn't put it here, so this is the book. You can look for the conjecture there. Okay, this family, it's really like pain in the ass. So basically, we know we know a lot about its K-stability. So, but not everything. So basically, what is this family? You take smooth cubic threefold, and you take a plain cubic curve, and you just blow it up. And then you have the Sarkisov link. So basically, map to P1 is just a projection from the linear span of this cubic curve. Yes, so, and then we prove some partial results. So basically, if you look for these fibers, so this map phi, it's a cubic vibration to cubic surfaces. So it's a simplest example of the Mori fiber space, which is basically Del-Pezzo vibration over P1 into cubic surfaces. And the fibers either dual, they all normal, either dual or maybe cones. In some very special case, they are cones. Yeah, of course, if you take everything to be generic, if V is general and cubic is general, then every fiber has just ordinary double, at most ordinary double point. Yeah, because it should be just basically like Lefschetz pencil. But in some particular cases, fibers can be quite singular, but we know classification of singularities of cubic surfaces. So we know all possible singularities of surfaces which are fibers of this map. So what we proved with Kent and Lena, we basically proved that delta invariant of x at a given point is bigger than 1 in all cases, except the case when the fiber which passed through this point singular at this point and has singularity of type D5 or E6. And this is very annoying because if surface has a worse singularity, like a cone, surface can be a cone with a vertex at this point, then it's very easy to estimate delta invariant, and actually estimate is very nice. It's bigger than 1. So if singularities of this surface that pass through this point are mild at this point, everything up to D4, then we also have estimates for delta invariant also bigger than 1. But for D5 and E6, all our estimates are not so good, and basically it means that technique which we're using has to be kind of adjusted, or so that it's actually purely technical difficulty. Difficulty is basically if you take this point on a threefold x and you blow up a weighted, consider special weighted blow-ups of x at this point, then we don't know how to find the risky decomposition of the pullback of anticanonical divisor when you subtract exceptional divisor with some coefficient. So we need to apply, for example, Abanjuan technique, we need the risky decomposition in the full range from 0 to the pseudo-effective threshold, but it's difficult in this case. Yeah, and okay, anyway, but maybe there are other methods. But this is very annoying because we basically almost proved case stability, and in this case, but with a few, yeah, and this is of course very special case. If for general threefolds in this family, this never happened. Okay, so okay, good. Next family is very explicit. So you take P3 and you take a curve of genus 5 of degree 7 and you blow it up. So in the book, we basically constructed very explicit such curve given by this, it's quite symmetric. It's actually has a symmetry of the group C5. We checked that this curve smooth and has a right genus, right degree. And using symmetries of this curve, we proved that if you blow up P3 in this curve, it's K-stable. The threefold is K-stable. So again, what the technical issues here? Technical issues here is that this defining polynomials of this curve is its ideal shift generated by cubics. So these cubics give you a map to P2. So when you blow up the curve, you resolve this map, and this becomes a conic bundle. So conic bundle over P2, and if the discriminant curve of the conic bundle is smooth, then one can use basically the same technique as we used in this symmetric case to prove K-stability. This is not done, but I'm pretty sure it should not be difficult. But when the conic bundle has singular like non-reduced fibers, so when conics becomes non-reduced, it may happen sometimes for special members of the family. This basically means discriminant curve is singular. And in this case, we have some technical difficulties to estimate delta invariant. And this happens in many families. So if someone actually realizes how to overcome this difficulty, how to estimate delta invariant for points in these non-reduced fibers, this would give a lot of K-stability for actually in many cases. Yeah, here we avoid doing this basically by using symmetries. Basically, this group which acts here, it's a cyclic group, but it has very few fixed points. So it's basically to estimate delta invariance, we only need to roughly consider them. And these points are nice. Okay, this is also done in the book. And we expect that all threefolds and smooth threefolds in this family are K-stable. 210. Okay, it's this family very similar to this family 2-5. It's actually, they have the same structure. You have a Delpezzo threefold and you blow up elliptic curve, which is intersection of two half anticanonical divisors. But in this case, it's a complete intersection of two quadrics. In the 2-5, it was a cubic threefold. Yes, and again, we can try to apply the same approach as in the family 2-5, but it's gonna break at some point. So the higher degree of the Delpezzo threefold, the weaker application. So the more difficult to prove K-stability. So in this case, we got very symmetric example. And yes, because it's very symmetric using symmetries, we immediately get, it's very easy to prove K-stability in this particular case. So in the book, this is what we did. And so which implies the general threefold is K-stable, and the automorphism groups of all smooth threefolds in this family are finite. So we actually expect that all threefolds to be K-stable. Okay, they all look K-stable. Okay, good. So 11, it's a blow up of cubic threefold in a line. Again, if you blow up cubic threefold in a line, you get a Sarkisov link, which actually give you a conic bundle. A projection from the line induce a conic bundle after blow up. And if this it's a ramification curve of degree 5. So if it's singular, we cannot get easily good estimates for delta invariant. But if it's smooth, it should be no problem. But this has not been checked yet, but I'm pretty sure it should be okay. But in the book, what we did basically, we consider very symmetric example. Yeah, very series of symmetric examples. So you have the group, I think C5, which acts here, and a very special line invariant with respect to this group, and then we prove K-stability just in one case. But it's a family. It's a two-dimensional family. But I'm pretty sure that proof now can be adjusted such that it should give the proof in every case when the discriminant curve of the conic bundle is smooth. This has not been done, but I don't think it should be difficult to do. And when the discriminant curve is singular, one needs some new ideas. Okay, good. 2-12, this is actually a very nice family, can be described in different ways, but one way it's a complete intersection of three divisors of degree 1, and P3 cross P3. Okay, and which is basically given by 3 4x4 matrices. So what we proved, we proved that if automorphism group is not cyclic or not dihedral, then it's K-stable. And it's easy to construct tones. And actually, we found all automorphism groups of this threefold. So, particularly, one example with a huge automorphism group is due to William H. He has actually a paper about this, and we can consider some very special threefold whose automorphism group is PSL27. It's like a simple group and a direct product with Z2. Yes, and in particular, it's K-stable. We expect all of them to be K-stable. And basically, one can use a Banjuan theory to prove estimate delta invariant. But the problem is you have two projections to P3, which are birational maps, blow up of the sexty curve of genus 3. And if you have this intersection of exceptional divisors, then all direct estimate application of a Banjuan theorem is actually doesn't work. Or only threefold. You actually have to apply this to the blow up of the threefold, but then you have other technical difficulties. But if you apply it, the technique to some flags inside the threefold that relate to point and intersection of two exceptional divisors, all estimates for delta invariant are very weak. So this is a problem, yeah. But if you have this condition on the group that there's no fixed point at the intersection of exceptional divisors, so you basically can prove K-stability very easily. Okay, The next family, so it's you take a smooth curve of genus 4, and basically it's a blow up of smooth quadric and a smooth curve of genus or smooth curve of genus 2. Yes, degree 6. So again, we needed a very explicit example of such threefold with a big symmetry group. So one way of doing this, to do this, we take a hyperelliptic curve, which is actually a double cover of P2 ramified on 6 of P1 ramified on 6 points, which are orbit of the S4. You have a group S4, symmetric group for elements which X on P1, and you take its orbit of length 6, take a double cover, and you have hyperelliptic curve whose automorphism group is the central extension of S4. And then you take triple canonical class, it embeds your curve as a sextic. Yes, and then it's not difficult to see that there exists G-invariant smooth quadric threefold in P4 containing this curve. You blow up this quadric in this curve, and you have this smooth Fano threefolds in this family with a relatively big symmetry group. And again, this is a conic bundle case. The second extremal array is a conic bundle. And we didn't check this in the book, but I'm pretty sure one can check that if discriminant curve is smooth, then of the conic bundle, then one delta invariant should be big. It should follow from a Banjuan theory. But for if it's singular, it should not work directly. Okay, as a conjecture, all threefold should be K-stable. Okay, good. So basically, okay, let me speed up a bit. So okay, since we're going to upload the slides to the web page, let me basically briefly scroll other families. So this is family 214, very similar to families which I mentioned. You take now smooth Delpezza threefold of degree 5, take it's Delpezza threefold, take twice intersection of two half anticanonical divisors, elliptic curve, you blow up, you have a fibration Delpezza surface of degree 5. And again, if you just try to prove directly, K-stability is difficult. We don't know how to do this. But if you have symmetric example, and we have very special cases, basically unique case, such that the threefold X has a symmetry of dihedral group of 10 elements. In this case, this dihedral group X without fixed points on P1, and then it's very easy to, using this, very easy to prove K-stability. Using estimates for delta invariant. Yeah, but without group action, we don't know how to do this. Okay. 216. Okay, this is in family, you take intersection of two quadrics and you blow up a conic on it. And again, you have a conic bundle given basically by projection of the linear span of the conic. And it was sort of tutorial problem on the K-stability school a few years ago. There was so many people. There was basically the K-stability school in Trento. There was a junior people, senior people, and senior people basically was learning. I was helping at the school as like a tutor. So we formed a big group of senior people who just want to learn this technique. And as an exercise, we basically proved. So if the discriminant curve of the conic bundle is smooth, then X is K-stable. And again, it's very similar technical difficulty when the curve is singular. Okay. So again, we expect that all of them has to be K-stable. Yes, 217, it's a blow up of quintic elliptic curve in P3. So what we proved with my friend Piotr Pakura, that if automorphism group of the threefold contains a group isomorphic to cyclic group of order 5, then X is K-stable. Again, basically in this case, group cannot X without fixed with fixed points on some exceptional set, and which helps. And now you can actually list all automorphism groups of the threefolds and construct tons of examples, but for non-symmetric examples, we don't know how to estimate delta invariant, and we expect all threefolds should be K-stable. Okay. Okay. So this is family 220 constructed in a strange way. So basically, it's intersection of it's a blow up of Delpezza threefold of degree 5 in a twisted cubic, and this is the we try to prove to find K-stable example in the book, but we failed to do this. So what we basically did, we took the unique threefold in this family with infinite automorphism group. And there's a one threefold in this family whose automorphism group is C-star semi-direct Z2. And this is basically a simple way how to construct it using the circuits of link, but we know it. One can show it's unique and it exists. An automorphism group is basically an extension of C-star. And in the book, we prove it's K-polystable. And then analyzing how the automorphism group on the tangent space to the reversal deformation, we actually prove that general member is K-stable. Okay. In this case, we don't know. This is the only example we know, which is explicit example, which we know that K-polystable. Oh, okay. Good. And okay, basically, let me like skip this. We upload to the web page, so people may look later on the web page description. So it's very detailed description of each family's remaining one. So I hope it may encourage some people to prove K-stability of all smooth members. Okay, let's, for example, consider this family. So we have very nice picture, but we don't know how to prove full generality. So, for example, what this is, you take P1 cross P1, and you have very explicit curve of degree 1,5 given by, and you can put a smooth curve of degree 1,5 and P1 cross P1, and given by this equation. You can put it into this form always. Yeah, and then you embed this surface P1 cross P1 into P1 cross P2 by Veronese. And yeah, and then you take this curve, the image of this curve on P1 cross P2, and you just blow it up. Family is very explicit, very, very explicit. Yes, and when you blow it up, this is Fano threefold and family 3,5. So if you take projection to the P1 of this threefold to this natural projection to P1, it's actually vibration into Delpezza surfaces of degree 4. So Denisova, my PhD student, she basically proved that if singular points of this vibration at most A1, then it's K-stable, but you can translate it into the language of this double 5-to-1 cover. Projection of this curve C to P1, first P1 with coordinate UV, it's a 5-to-1 cover. So if ramification point are all simplest of index 2, then it's K-stable. But in general, and basically here, it's very clear to see the link to GIT. And using GIT, you can produce non-K-polystable examples, but K-semi-stable. So in the conjecture, it's threefold is K-polystable if and only if the curve is GIT stable with respect to PGL2 square action. So this is very, very explicit case. Yeah, but it would be very interesting to solve it. Okay, prove it. Okay, so okay, I'm a little bit out of time. Let me just scroll everything. Maybe go to the last family is very interesting. So let me just mention this. It was basically the last family we did in the book, which is actually not, the proof is not contained in the book because it was basically done by Kenta Fujita, so he wrote a separate paper about this. So you take a quartic elliptic curve in P3, you take a point on the curve, you blow up the point, and then you blow up strict transform of this curve. And this is Fano threefold in the family 311. So it's moduli, it's basically a moduli of elliptic curve and elliptic curve. Yeah, choice of point, two-dimensional. So there are exactly one-dimensional subfamily here with threefolds with a non-trivial automorphism group, and among them there are two threefolds which are very symmetric, relatively very symmetric. Groups are C6 or C4. So which correspond to the curves with the complex multiplication. So we took one of this. We actually in the book we took two threefolds in this family, very explicit. And we try to prove that they K polystable, we fail. And then after maybe a few months, Kent Fujita proved that one of them is K polystable. Proof is very involved. So basically we knew only one explicit example, but since automorphism group of all smooth members here are finite, we know the general member is K-stable. Yeah, but recently Robert-Smith proved that basically opposite in some sense case when automorphism group is trivial then it's K-stable. So it's more or less proved it's a complementary result. So now we need to deal with a one-dimensional subfamily. Yeah. Okay, so basically, this is what I all wanted to say about smooth Fano threefold. So I really want this to be finished in the nearest future. But let me briefly mention about what's some problems in about singular Fanos and also about some high-dimensional case, which I think it's a very natural problems. So first, of course, question of moduli, but let me scroll this because it's overlap with Salt Lake City a bit. Singular limits are the first case when we have to consider singular K polystable limits, singular Fano threefolds, which are naturally arise in this problem. Okay, another natural class, historically interesting and also very natural from different problems, not only from this problem. It's Johnson-Kohler threefolds. It's basically second paper of Jennifer and Janusz, very similar to Del Pezza, but now for threefold. So if you take a well-formed quasi-smooth hypersurface of index of degree D and index 1, Johnson and Kohler basically classified them. They show that there's exist 25 infinite series, very explicit, and 4,442 sporadic families. A lot, yeah. And then basically Janusz gets some very nice method how to like some inequality between the weights which guarantee that alpha invariant is bigger than 3 or 4 in this case. So then it works for approximately half of sporadic families. Yes, okay. And very recently, okay, there's a special subcases here when threefold has a terminal singularity. These are exactly 95 families. These are 95 among sporadic examples. And they're usually called Reed and Fletcher. And very recently, it was proved that all quasi-smooth threefolds in these 95 families are K-stable. It's basically paper, I think it was last year. It was many results in this direction, first for generic, and then for some, and then for all. Yes, and my expectation that all Johnson-Kohler threefolds, I mean quasi-smooth, well formed, all gonna be K-stable, but this is open. Okay, I'm a bit over time, but let me just list another very nice class of high-dimensional varieties to be considered, which is actually a natural extension of Fano threefolds, which are called Mukai varieties. Sometimes people call Fano Mukai varieties or Mukai varieties. So it's basically Fano varieties of K-index 3. So Mukai proved if Picard rank is 1, and if it's not weighted complete intersection, then starting in dimension 4, I forget to mention this is dimension 4 and higher, we have very few cases. Yeah, no, this is including dimension 3 as well. Very few cases, and of different dimensions. And then you can take hyperplane sections and you can lower dimensions. So for example, G is equals 6. It's also known as Gushel varieties or Gushel Mukai varieties of Gushel Fano varieties. Yeah. So this is a very nice class. And also we have a special, we have the same list for Picard rank 2. Yes. Okay. And as far as I understand, for Mukai fourfolds, for example, it's a very natural class. First, it was not considered K-stability at all, except basically two results. One result is this blow up of quadric fourfold along the conic. I mean, some non-trivial results. It follows from Thibaut de Lacroix paper. And unpublished theorem by Kenta Fujita that one of Mukai folds of genus 10, I mean this one, the most symmetric one, is K-stable. We plan to work on this with Kenta and with Prokhorov, but while discussing this, Kenta already proved one case, this one-dimensional family. Yeah, and one is actually not polystable because automorphism group not reductive. Okay, sorry, I'm a bit over time. Okay, let me stop.
Thank you. Any questions for Vanya?
So for this family 3.5, are you expecting some kind of like modular relationship between the
Moduli, okay, let me go to 3.5. We have actually several examples like this. Let me consider the family, which is actually
3.5.
Yeah, let's do 3.5. Okay, wait. It's wait. I cannot. Oh wait. Okay, this one. Yeah, we expect that if smooth one, if it's JIT stable, then if it's JIT stable, we expect it should be K-polystable.
No, I mean it seems the last conjecture you made seems to be related to the modular of the threefold to some modular terms.
Okay. So I'm not sure that if you consider if you take a reducible component of K moduli of these three folds, and if you take just JIT quotient for this curve, I'm not sure it's going to be the same thing, but it's definitely related. But for at least on the smooth locus, for smooth three folds, I believe it should be the same. And actually, this okay, this is actually related to moduli of V22. Why? Because, for example, when you blow up this curve, you take this surface S, take its preimage, you can contract it, and you get V22 with one singular point. So in some sense, this should be but singular. So in some sense, moduli of this threefold, K moduli of this threefold should be definitely, at least clearly birational to the one component of the K moduli of this basically boundary complement in the K moduli of V22 to the smooth ones. So this should be maybe linked to this. Maybe actually it's the all components. Maybe actually it's all of them. It's in the closure of this one. Yeah. Okay. But for JIT stability, for link for relation between K moduli and JIT moduli for these curves, I don't know that they're equal. Maybe we need to blow up because some curves can be which actually I don't know. Actually, it's currently work in progress of Lena Denisova and Theo, former student of Jesus, who is now in Beijing. They actually discussed on this. So far, all curves that looks all JIT polystable curves looks like they give K polystable threefolds. The only problem is that we don't know how to prove this, even for smooth ones. Yeah. Did I understand your question correctly, Chinyank? Yeah.
Oh yes. I mean, well, I mean, usually, if you can guess what the modular is, then there might be some like modular comparison approach instead of just directly computing the delta event.
Yeah. So yeah, in this case, actually, degree is quite large, so one can probably prove it using this technique using the generation of K3s and okay.
Other questions? So if not, let's thank Vanya again. And let me stop the recording.